Hey, greetings 347 fans. Second clip on more general solution methods to higher order differential equations. In this video, we'll have a look at variation of parameters as well as reduction of order. Variation of parameters turns out to be a more general strategy for finding a particular solution, and reduction of order is a strategy for finding a second linearly independent solution to a differential equation given a solution. Okay, without further ado, variation of parameters. So as I mentioned, we know how to find a particular solution using the method of undetermined coefficients. We saw that the method of undetermined coefficients can apply to the constant coefficient non-homogeneous differential equation for some source terms f. So in particular, we saw that the method of undetermined coefficients applies when the right-hand side, or what we're referring to as the source term, is a polynomial or an exponential function or sines and cosines. So variation of parameters is a similar method. It's a strategy for finding a particular solution. However, it applies to a more general linear differential operator, right? So here we have a more general linear differential operator Lx, x double prime plus p of t x prime plus q of tx, and as well more general sources f. Okay, so as you might imagine, with this expanded scope of more generality, there's a cost, and that cost turns out to be more differential equations to solve, or actually more antiderivatives to do, as it turns out. So let's dive right in. Here is the main strategy. The main strategy is that the general solution to the corresponding linear non-homogeneous differential equation, x double prime plus p of t x prime plus q of tx equals f of t. We know that the general solution to that differential equation has form of xh plus xp, where xh is the solution to the corresponding homogeneous equation, and xp is a particular solution. Okay, so once again, if we can find a fundamental set of solutions to the corresponding homogeneous equation, we'll take xh to be c1x1 plus c2x2. And then all that remains is to find a particular solution. So this is where variation of parameters jumps off. Variation of parameters says, let's try, instead of a linear combination of x1 and x2, a nonlinear combination of x1 and x2. Okay, so here our functions u1 and u2 are not constant, they're functions of t. Okay, so we sort of use the intuition that the solution to the differential equation, the particular solution, should be related somehow to those functions which are the solution to the corresponding homogeneous equation, and then we'll just see what happens. So things get a little bit crazy here when we plug in the solution u1x1 plus u2x2. In order to plug that in, we need the second derivative, which is here. This turns out to be the second derivative. We need the first derivative, and that's here. And then, of course, we need the function itself, and that's here. And as we've done before, what we'll do is go ahead and collect these terms up according to the functions u1 and u2. So you can imagine that u1, for instance, has an x double prime attached. It has p of t x1 prime attached, and it has a q of t x1 attached. There's some more stuff too. So when we collect up the u1s and the u2s, we end up with this expression. Now, this is unwieldy and fairly messy, but I will point out that there are a couple of things here that are going to make our life easier. One of those things is this this term u1 x1, u1 prime x1 and u2 prime x2. That comes up twice, as you can see. Okay, and the other thing that I'll point out are these expressions attached to the u1 and u2 that look just like the left-hand side of the differential equation. Okay, in fact, those are exactly the linear operator L applied to x1 and x2. Now remember that x1 and x2 form a fundamental set of solutions. They're solutions of the homogeneous equation. So therefore this term is 0, and so is this term, as it turns out. So with the assumption that u1 prime x1 plus u2 prime x2 is 0, this expression reduces significantly, and again, that term pops up twice. It pops up here and here. So we just take that to be 0. Let's choose u1 and u2 such that that expression is 0. Then all we're left with is lxp equals this term involving u1 prime x1 prime and u2 prime x2. Now, what we really want here is for xp to be a solution of the homogeneous equation. So what we really want is for lxp to equal f of t, whatever that f is. And as you can see, if we can choose u1 and u2 so that this expression is equal to f, then we're done. So that, as it turns out, is the second condition here. So the first condition is that x1 prime x1 u1 prime. Sorry about that, I was interrupted by a phone call. In any case, here's our system, x1 u1 prime plus x2 u2 prime equals 0, and x1 prime u1 prime plus x2 prime u2 prime equals f of t. Now this is sort of a scary looking system, but first glance maybe, but it's really not. It's just a linear system for u1 prime and u2 prime that we can solve because we know x1, x2, and f. So all we have to do is solve this system for u1 prime and u2 prime, use antiderivatives to find u1 and u2, and then go ahead and express the particular solution as that nonlinear combination of x1 and x2 now that we know u1 and u2. And the way we typically solve this system for u1 prime and u2 prime is by using Cramer's rule. So here is Cramer's rule applied to that system to get an expression for u1 prime and u2 prime. So here I've expressed u1 prime as a quotient of determinants, as well as u2 prime as a quotient of determinants. Okay, so those quotients are here. And when you go ahead and take those determinants, check out the handout online for a little bit more on 2x2 determinants. We identified the denominator there, the common denominator in both terms, as the Wronskian. It's the 2x2 determinant of the zeroth and first derivatives of those fundamental solutions. Now it turns out, and we won't prove this, but you can, that the Wronskian is never 0 as long as x1 and x2 are a fundamental set of solutions. So we know that we can always express our solutions this way. Again, one more step required, and that one more step is to integrate up those particular, those u1 and u2 primes. So here, this is antiderivative of u1 prime, and this is an antiderivative of u2 prime. Integrate those up to find out u1 and u2, and then again express a particular solution as u1x1 plus u2x2. Okay, so that's kind of a lot, but this last slide is sort of the take-home message that u1 and u2, their derivatives always act like solutions to this linear system, and we can find that linear system by looking at a quotient where the denominator is given by the Wronskian. Okay, so let's go ahead and look at a couple examples. So here's the first example. Let's use variation of parameters to find a particular solution to this constant coefficient second order non-homogeneous differential equation. Now, this is an equation that we can solve using our old methods, using the method of undetermined coefficients, but we'll go ahead and use variation of parameters here and see how that turns out. So the first thing that we need for variation of parameters is a fundamental set of solutions to the related homogeneous differential equation. Okay, so we know how to solve that homogeneous differential equation. Try a solution of the form e to the lambda t, identify the characteristic equation, and in this particular case, we have real distinct roots. Those roots are -4 and +3, giving rise to a fundamental set of solutions e to the -4t and e to the 3t. Okay, so now we'll go ahead and for the particular solution, before we do that, excuse me, we'll identify the Wronskian. So again, the Wronskian is the the determinant of the zeroth and first derivatives of those fundamental set of solutions. And again, here we just take the product of these diagonal elements, and then take the product of the off diagonal elements and subtract the 2. So when you do that here, in this case, you get 7 times e to the minus t, and we'll use that here in just a minute. Okay, so for the particular solution, we'll try a solution of the form u1x1 plus u2x2, and as we saw before, the coefficient functions satisfy this linear system in u1 prime and u2 prime, where the forcing function here given by e to the 3t falls into place here. Okay, so we'll go ahead and use our Cramer's rule to solve this, expressing the first as e to the minus 3t, e to the 3t times e to the 3t over the Wronskian with a minus sign, which turns out to be negative 1/7 e to the 7t. Integrate that up to find out u1. And the second, as it turns out, is just plain old 1/7, which we integrate up to find that u2 is 1/7 t. Now, here's a particular solution. Again, the particular solution is u1x1 plus u2x2, and the form you can see here. Okay, so this is sort of as we'd expect from our intuition by method of undetermined coefficients. We would expect there to be a term that has form of t e to the minus 3t, and that's here, and this e to the 3t term, as it turns out, is sort of a byproduct of the method of undetermined coefficients that is just sort of an extra part of the solution to the corresponding homogeneous equation. So keep in mind that you can always add a solution of the homogeneous equation to any particular solution, and it gives us a particular solution again. Okay, so a second example, here's an example of a differential equation where the forcing function, the right-hand side, is something we don't know how to deal with, so a secant in this case. Okay, so we'll start off the same way, finding a fundamental set of solutions to the related homogeneous equation, trying xh equals e to the lambda t, identifying the characteristic equation lambda squared plus 9 equals 0, so that the the purely imaginary roots are plus or minus 3i, which gives us a fundamental set of solutions, cosine 3t and sine 3t. Go ahead and quickly identify the Wronskian. Here's the Wronskian again. It's just the quotient or the determinant of the zeroth and first derivatives here of those two fundamental set of solutions, those two solutions from the fundamental set. And in this case, that simplifies nicely as just 3. Okay, so the Wronskian of these solutions is 3. We'll use variation of parameters to find the particular solution, and again here we'll try a particular solution of the form u1x1 plus u2x2. The coefficient functions u1 and u2, their derivatives at least, satisfy this equation, and there's a typo here. This should be secant, 3 secant of 3t, right? That's the forcing function in this particular case. Okay, so go ahead and solve that with Cramer's rule, and once you do, you see that u1 prime turns out to be negative tangent of 3t, and u2 prime ends up being just 1. Now, tangent isn't something that we integrate up a lot in this class, but it is a Math 162, and I'll remind you that in this particular case we can write the antiderivative of negative tangent as 1/3 times log of the cosine. Of course, antiderivative of 1 is just t, and plugging these in to our form for the particular solution, we can see that the particular solution is nothing like anything we would guess, right? There's no way that we would guess to multiply cosine times the log of cosine, but that turns out to be the particular solution in this case. Okay, so this is sort of the power of variation of parameters, that it gives us a more general strategy for finding particular solutions, just so long as we can do a couple antiderivatives. Okay, one last comment here is that this variation of parameters formula applies to the non-homogeneous linear differential equation Lx equals f. In particular, we have to have the differential operator in sort of that second order linear normal form, where the coefficient of the second derivative is 1. So as you go forward in your life, like when you do your homework, you'll find a couple examples where that coefficient function is not 1. For instance, here is a differential equation t squared x double prime minus 2tx equals t cubed, a non-homogeneous differential equation. In order to identify Lx so that Lx is in that sort of second order linear normal form that we've used for variation of parameters, it turns out you have to divide through by this factor of t squared. And when you do that, we'll associate x double prime minus 2 over t squared x with the differential operator, and the forcing function that goes into our variation of parameters formula for Lx equals f turns out to be the right-hand side t, right? So it's not t cubed here. It looks like the right-hand side is t cubed, but keeping in mind that we need that forcing function to have to be associated with the differential operator whose coefficient function is 1, we can see in this case it's t. Okay, so keep that in mind as you work through these problems, that you need to make sure you have what we'll identify as, I guess, second order linear normal form. Okay, final topic of this video is to talk about reduction of order. Reduction of order is a strategy for finding a second linearly independent solution to a differential equation given 1. So sort of related to variation of parameters in that we'll try something that's a non-scalar multiple, right? A non-constant multiple v of our known function x1. Okay, and what we do here is just plug that function in and see what happens, right? So we'll go ahead and recast our differential equation as Lx equals 0, homogeneous equation. Substitute in x2 to obtain a differential equation for v, and then once we can solve that differential equation for v, x2 is equal to vx1. Okay, so here's an example of variation of reduction of order on a differential equation we know how to solve. So we know, for instance, that e to the minus 2t is the solution to this differential equation. And to find a second solution, we'll try one of the form v times e to the minus 2t, right? So this is equal to v times x1. When we do that, we can plug in our solution x2, and you're going to use some product rules here. So x2 prime and x2 double prime are here with the product rule. And it gets a little bit messy when we plug this in, but these things can always be reorganized in terms of the second derivative of v, the first derivative of v, and the zeroth derivative of v. And what you can see in this case is that the zeroth derivative of v vanishes, as well as the first derivative vanishes. Okay, so again, this is just nothing more than substitution and simplification. So we see that x2 is a solution if v double prime times e to the minus 2t is equal to 0. Okay, so it turns out that this is an equation we can solve quickly for v. Of course, that's the same as saying that v double prime is equal to 0. And if v double prime is equal to 0, of course, v is just some sort of first order function in t. And if v is a first order function in t, we can choose c1 and c2 to be as simple as possible, keeping in mind that x2 should be linearly independent from x1. So the way we'll do that in this case is by choosing c1 equal to 1 and c2 equal to 0, giving us that v of t is equal to t, so that x2 is equal to t e to the minus 2t. So I've been promising you this for a while, that we would be able to identify the second linearly independent solution in this case of a constant coefficient equation where the eigenvalues of that differential equation are repeated roots, and you can see here how we find it. Okay, that same strategy applies to Cauchy-Euler equations too. Here I just make that same comment I just made, that the real repeated root comes up here, and we see how to get that by reduction of order. Okay, so this applies to Cauchy-Euler equations too. So here's a Cauchy-Euler equation that we will solve for a second solution, and it should be here that that x1 equals t squared as a solution, not t. This should be t squared as a solution. Okay, so in any case, here I'll do this in a little bit more generality. Instead of substituting t squared in, I'll just leave it as x1. So the zeroth, first and second derivatives are given here, just using the product rule. And when we substitute those into the differential equation and reorganize, again, categorizing things in terms of v double prime, v prime, and v, one of the things we see is our differential operator jumping out at us. Okay, so that's just a result of the product rule, but it turns out that when x1 is a solution, that term is always 0. Okay, so this term is going to reduce to 0 quickly, and once that happens, we see sort of the name of reduction of order, that the order of our differential equation reduces quickly to something lower. Okay, so in this particular case, Lx2 is 0 if this quantity is equal to 0, and even though that looks like a second order equation for v, it's really a first order equation for v, for a first order equation in disguise here, I guess. So I take u to be v prime, and here is the related first order equation for u. We know how to solve first order equations. Solve that however you want to. In this particular case, I'll just go ahead and use the integrating factor to say that tu has to be a constant. Of course, if tu is a constant, remember that u is v prime, then t times v prime has to be a constant, or v prime has to be a constant over t, giving us that v is equal to c1 log of t plus c2. Now, once again, we'll choose c1 and c2 as simple as possible, leaving x2 linearly independent from x1. And again, in this case, we'll go ahead and take c1 to be 1 and c2 to be 0. And when we do that, we find that second solution, t squared log of t. Again, here, x1 should be t squared, not t, so I apologize for that typo. But that's the second linearly independent solution that you would expect to find in the case of a repeated root for a Cauchy-Euler equation. Okay, so I hope you've enjoyed this video on variation of parameters and reduction of order. We'll do some more examples involving these two strategies in class. So long for now. We'll see you soon. Bye-bye.